Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I'm very happy to have Mohamad Ali-Dib with us today. Hey, Mohamad.
Hi, Frank. Thank you for having me.
Well, thank you very much for being willing to talk about your really lovely AJ article. What's your geolocation? Where are you at?
So right now I'm spending summer in Lebanon, where I grew up.
Ah,
so
cool.
yeah, I'm on the other side of the world where the weather is nice, but things are a bit complicated right now. So the internet is sketchy, the power is non-existent, and yeah, it's in the middle of political change, let's call it this way.
Yes. I do keep up with the international news. Well, Lebanon, I think you win the prize for the first person doing one from Lebanon. So thank you. That's awesome. And yeah, we do have a little bandwidth lag, people. So just bear with. It's all good. The astronomy will be great. It's well worth your plowing through some of the bandwidth lags, perhaps. So yeah, it is July 27th, 2021. I'm in Phoenix, and it will be a usual late July day in Phoenix. So it'll be quite hot. We'll get up to about 43 C, somewhere around there or so. What is the temperature where you're at in Lebanon in the summer?
So right now I'm in the countryside, so it's like about 29 degrees.
Ooh,
it does
nice.
get much hotter on the coast.
Ooh,
but
okay.
Where I am, the temperature is pretty okay.
Very nice. So cool. Mohamad, what do you like to do for research?
Yeah, so I work on planet formation theory. I got my PhD in 2015 working on formation related stuff and protoplanetary disks, volatile transport. The origins of chemistry, the origins of giant planets chemistry was really my thing. I started doing solar system small bodies recently, and this paper is really part of that. I also do some machine learning on the side, but that's not today's topic. So mostly planet formation.
Yeah, no, it's about your research. So machine learning is something you like. That's great. It's certainly very certainly a very hot topic in astronomy these days.
Yeah,
a lot for
absolutely
a lot of things these days. So that's really great.
Absolutely
very cool. So that is going to bring us to this very lovely AJ article on the rarity of very red Trans-Neptunian objects in the scattered disk. And Mohamad, take us away.
Yes, so this is a project that actually took me roughly three years to finish. So it's really a long-term. It was really a long-term project.
Right.
The paper itself, it has two parts. The first part, which is, I don't know, 1/3 of the paper, I would say, is observational, where we look at archival data and we reanalyze this data. And in the second part of the paper, which is theoretical, so we do embody simulations to interpret this data. So the main idea, so the take-home message of the paper is that if you look at the eccentricity, so the eccentricity is the new thing we bring into this into the field, but also the inclination, but this has been already known. If you look at the eccentricity and the inclination of Trans-Neptunian objects, of TNOs, these are very correlated with the color of these objects. So it has already been known that there is a color inclination correlation in TNOs. But what we also show first using this archival data is that there's also an eccentricity color correlation in TNOs. And then the second part of the paper, we use theoretical models to try and explore and explain what's really happening from a formation point of view.
Right. Very cool. Nice. Very cool.
So maybe maybe we can start with figure 1.
Let's do figure 1. We got our intro here.
Yeah, so figure 1 is the I would say it's the most important observational part figure. So so if first we start with the right hand panel, so the inclination versus the spectral slope. What we have here is well, obviously observations. So observations mostly from the Colossus survey, which is a French-Canadian survey that's where they are trying to observe the colors of TNOs, but it's supposed to be a survey where the observational biases are well modeled.
Okay.
So in a sense, we understand the observational biases in the survey, and so it's easier to get general trends and conclusions about the overall population that you are observing without really being paranoid about whether you have some observational bias that's really messing things up. So the right-hand side is something that has been known for a few years now, which is if you plot the inclination of TNOs of, well, hot TNOs, they are hot since the minimal inclination you see here is 5 degrees.
Mm-hmm.
So if you plot the inclination versus the spectral slope, which is the color, the surface color of these objects, you can see that
yes,
objects with inclinations above 21 degrees are mostly gray. So just a bit of a disclaimer. I'm gonna be using the terms gray and red to talk about the colors of objects, but in the paper we refer to these. So we refer to red objects as very red, and we refer to the gray objects as less red, which is technically correct, which is technically more correct, but just to make things easier right now, I'm gonna use gray for less red objects and red for very red objects. So if you look at the right-hand panel, you can see this vertical dashed line around the spectral slope of 20 roughly. Everything left to this line, these are gray objects.
yes.
And everything right to this line, these are red objects.
Okay.
So yes, so it turns out that almost all of the objects with inclinations higher than 21 or 22 degrees, these are gray objects. So you have very, very few red objects on high inclinations. So this was a known result from 2009 from Marseille et al. Mm-hmm. However, the new thing that we discovered from reanalyzing this data is the left-hand side, which is if you plot the eccentricity versus the spectral slope, so the eccentricity of this very same data set versus the color of these objects, then you have the exact same trend. So we can see that objects with, or TNOs with eccentricities higher than 0.41 roughly are also almost exclusively gray. So you have very few red objects on eccentricity higher than 0.42.
Right.
Now, if you keep looking at the left-hand side and you look at how these objects break down by family, so you look at the labels, you can see that the majority of these objects, so these gray objects with eccentricity higher than 0.42, they are mostly scattered disk objects, right, which is really by definition. So the scattered disk objects have high eccentricity, and most high eccentricity objects are scattered disk objects by the very same definition of the scattered disk. Yeah. But also on top of these, you add some mean motion resonance objects, but these are very high order mean motion resonance, and so these coexist within the scattered disk. Yeah. So what the left-hand panel is telling us is that, well, the scattered disk and all of the TNO families that coexist within the scattered disk are gray objects, the vast majority, and you have very few red scattered disk objects. So this is really the title of the paper, which is the rarity of red objects in the scattered disk. And this really can be seen in this left-hand panel. Mm-hmm. Now, if you compare this to the right-hand panel, you can see that the high inclination objects in the right-hand panel, these are much more diverse. So, so high inclination objects are not necessarily part of the scattered disk, right? And so the high eccentricity objects and the high inclination objects, these are not the same objects, right? So you have different populations.
Yes.
That are behaving somehow in parallel and creating these two correlations. where the high eccentricity and high inclination objects, who are not the same objects, both are very predominantly gray. And so this was really the conclusion of the observational part,
Cool.
which is, so actually we can see this easier in figure 2 in the left-hand panel of figure 2.
Sure, figure 2.
Yes, so in the left-hand panel of figure 2, you can see that red objects are dynamically very constrained to eccentricities less than 0.41 or 42 and inclinations less than 22 degrees. So this is really the conclusion of the observational part of the paper, that the red objects, the red TNOs, are dynamically boxed, right? They are constrained to the interior of this box with a given eccentricity and a given inclination.
Got it.
So this is really the, well, let's say this is the main observational result, even though there are other stuff that we might come back to later.
Okay.
So this was what we were trying to explain theoretically in the Embody simulations, which is why is this the case. So how do you how do you make a Kuiper belt where the red objects eccentricity and inclinations are so limited and very sharply limited, I would add.
Yeah, that's a pretty pretty sharp dividing line relatively. Yep, very cool. Okay, I'm with you.
Sure. So I'm gonna move to the theoretical part, and then maybe we'll go back to the observational part, but let's just move on to the theoretical part. Okay. So maybe figure 4, maybe you can go forward to figure 4.
I will go forward to figure 4. And wait for our bandwidth to catch up.
Yeah, so the way we try to interpret these results theoretically is using embodied simulations. So these are really standard in the solar system formation community. So you start with the 4 giant planets. You have Uranus and Neptune, usually on slightly or more than slightly compact orbits. So they are usually on smaller semi-major axes. And then you put some planetesimals disk outside, well, massless planetesimals disk outside the orbit of Neptune. And then you add some force that mimics migration. Okay. You slowly migrate Uranus and Neptune outward to their current orbit, and you let the entire system evolve. So that's how you really create the Kuiper belt theoretically. Are you with me? Okay, perfect. So in this set of simulation, we start Uranus roughly around 15 AU. We start Neptune around 21 point something AU on a given eccentricity and inclination. Jupiter and Saturn are on their current orbit, more or less. Okay. And we throw roughly 10,000 planetesimals around Neptune with a given distribution. So a given and inclination distribution. Okay. And we migrate Neptune outward on a 60 million year time scale. So the 60 million year time scale is important because earlier work by David Desvorny and others showed that the slower the migration of Neptune is, the higher the final inclination distribution of TNOs become. So to match the inclination distribution of TNOs, the observed inclination distribution, you really need a relatively slow migration timescale for Neptune, which is why we chose this 60 million years.
Got it. Good. Good.
Okay, perfect. So this is really our setup. It's a slowly migrating Neptune outward with planetesimals disk, and you let the whole thing evolve. Now, the question is, how do we introduce colors into this scheme? How do we, so we obviously want to study the correlation between the color and the orbits of these particles. So how do we introduce the color?
Right.
The fundamental hypothesis, really the fundamental idea is that we are assuming that the colors, or in this case, really the surface colors of these objects, are inherently tied to where these objects formed. So gray objects formed in a given location, formed in a part of the planet of the protoplanetary disk, and red objects formed in another part of the protoplanetary disk.
Yeah.
So the surface colors of these objects is directly tracking where these objects formed.
Okay.
So we are assuming that the colors are primordial. They are not due to some surface weathering or any surface related effect. They are fundamentally tied to where these objects formed.
Okay.
So so the idea is to introduce a color transition line. So we choose some distance in the disk, some semi-major axis value, inside of which we assume that any object that formed, any test particle that started on a semi-major axis smaller than this color transition line is gray and will always remain gray. And any particle that formed outside of this color transition line is red and will always remain red. So this is really our setup. It's a classic Neptune outward migration setup, the planetesimal disk, where we assign each particle a color simply based on its initial semi-major axis. And the location of the color transition is a big parameter in the model. It's one of the main free parameters in the model.
Sure. Yep. I got it. I'm with you.
Okay, perfect. So before we look at the colors, so before we try to understand the question of the colors, let's first make sure that our model is reproducing the orbits, right? So we want to tie the orbits into the colors, but let's start with the orbits just to make sure that we are reproducing the Kuiper belt as we observe it, or at least as close as possible. So we are not really far from observations. Let's go to figure 5, the bottom 2 panels. So the bottom 2 panels of figure 5.
Okay. And we're just
the bottom panels of figure 5 show the cumulative eccentricity and inclination distributions, both for our simulation,
all right,
and for the observed and for observations. So the red lines are the cumulative eccentricity and inclination distributions, and the blue lines are the simulated eccentricity and inclination distribution. So there isn't a lot to say here other than we fit the eccentricity and inclination distributions well. And this is what you really want, right? So you really want to start from a solid result where you know that you are at least reproducing the main aspects of eccentricity and inclination of the NOs, and this is what's happening. You can see the blue lines and the red lines are pretty close, and well, so that's how we know that our model, at least from a orbits point of view, is reproducing the Kuiper belt relatively well. So with this in mind, we can start looking at the colors. So let's go to figure 6.
Okay.
So we need both rows.
Yep.
Perfect. So the idea of figure 6 is the following. So the idea is that, so the idea behind the main idea of in the paper is that the color of the NOs are set completely by where they formed. And so, as I said, we define this color transition line inside of which objects are gray, outside of which objects are red. And a central And the central question of the models we develop is, or of the paper itself is, can we localize this color transition line? So given our hypotheses, can we really say that this is where in the protoplanetary disk, where these objects formed, this was the line that separated the gray objects and the red objects. And this is really what we try to do in this plot in figure 6. So if you remember a few minutes ago, we said that the main observational result can be summarized as the red objects being dynamically constrained to inside 21 degrees inclination and inside 0.42.
Yes.
So what we are doing in this plot, in this figure, is we are taking exclusively the red objects, so exclusively the simulated red objects, and we are choosing 4 different color transition lines. So all the way on the left, we choose a color transition line at 38 AU, then 40 AU, then 42 AU, then 44 AU. And we plot the eccentricity and inclination distributions purely for the red objects. So what we want is we want to see which color transition line produce all very few to none red objects outside of the observational limit inclination and eccentricity. So you can see these limits in the vertical dashed blue line. So this is the in every panel there's a vertical dashed line, and these are and this is the observational limit. So observationally, we know that red objects are constrained to eccentricity and inclinations to the left of these dashed lines. So basically what you want is you want a color transition where the right-hand side of this dashed blue line is almost empty. Right. So, or at least something interesting is happening. So if you look all the way to the left at 38 AU, you can see that the inclination distribution is continuous, right? Nothing is happening at 21 degrees inclination. Okay. The distribution is continuous. And if you look at the bottom left, at the eccentricity, you can also see that while the eccentricity slope is changing at around 0.4, which is what you want, the number of red objects with high eccentricity is still relatively high. Right. So I wouldn't say this is really satisfactory. Now, if you go all the way to the right to 44 AU, so any objects formed inside 44 AU is gray, outside is red, and you can see that outside of 21 degrees, there are almost no red objects, and the same is for outside of 0.42 eccentricity. The problem with 44 AU is that this value, this transition is not consistent with other observations, mainly the colors of the classic cold belt, which is not part of this data set. So this data set is for objects with an inclination of at least 5 degrees, the observational data set. And if you add on top of this the cold object with lower inclinations, then 44 AU color transition is not consistent with those observations. So we are left. So we are left really with roughly 42 AU. So 42 AU is as far as we can go, and this is really the value we adopt in the paper. So in the paper, what we are claiming is that to reproduce this eccentricity inclination cutoff of red objects, dynamical cutoff of red objects, you need a color transition line around 42 AU, which is relatively far, right? I mean, if you want to think about this color transition line as a snow line or any chemical structure in the disk, 42 AU is far. I mean, most observed chemical structures in the disk are usually closer, which is really interesting. Right.
As though it were a snow line. Right. Very cool, though.
Yes.
Okay. I'm with you.
Yes. So now let's go to figure 8, the middle panels, just the middle panels.
Figure.
So the inclination panels.
Yes.
Okay. Yeah, that's good. That's good. So we're talking about the inclination panel. So initially we were happy with this color transition at 42 AU. We said, well, it seemed to be explaining observations reasonably well, and we were happy with our result. But then we noticed something that, well, we initially didn't really see, and it actually changed it changed really the scope of the paper entirely, which is the following. Which is the following. Any color transition at 42 AU, while it does lead to a rarity of red objects in the scattered disk,
yes,
which is exactly what you want.
right.
It also lead to an almost non-existence of red objects in other structures objects. So what I'm talking about mainly is the 3-2 motion resonance with Neptune.
Sure. Okay.
So the 3-2 motion resonance with Neptune, it's around 39 AU. It's what we call the Plutinos. It's where Pluto is, and it's all of the objects that are in the same resonance as Pluto. These are called the Plutinos, and these are very well observed. And if you look at the left-hand panel, so the left-hand panel is showing only red objects, both in the observations, which are the blue squares, and in our model, which are the red circles. So both of these are only red objects. You can see that around just inside of 40 AU, there is this line of blue squares, right? And all of these blue squares, these are objects observed these are Plutinos, so objects in the 3-2 motion resonance with Neptune that are all red objects. And our model does not create almost zero such objects. And this is purely due to our color transition line being really far at 42 AU.
Yes.
And so it turns out that there is this paradox, really, which is to create these red objects, these red Plutinos at 39 AU, you need the color transition line to be around 37, maybe 36 AU, which is really far in. But then your scattered disk is going to be almost entirely red, or very large fraction of the scattered disk is going to be red.
Correct. Yes.
And on the other hand, if you bring the color transition line to 40 something AU, then the scattered disk colors are reproduced correctly, but then you do not reproduce the right colors for the Plutinos, for the 3-2 mean motion resonance. So the color transition line is either far out and then you reproduce the scattered disk properly, or close in and then you reproduce the Plutinos properly, but not the scattered disk. And so we thought that maybe this is really just due to some parameters in the model.
Right.
And this was also suggested by the referee that maybe it's due to the surface density profile of the planetesimals. Maybe our surface density profile for the the test particles is too shallow. It's not it's not sharp enough. And so I will not be talking about those figures, just not to go out of time, but we explore this thoroughly in the paper. So these are the last most figures that I will not go into right now.
Okay.
But this is not the solution. We explored 3 or 4 different initial semi-major axes, and this tension, this paradox persists. We explored what we call a granular migration versus smooth migration, where Neptune's migration is jittery instead of being smooth.
Yeah.
And this does not solve the problem. We explore different initial eccentricity and inclination for the planetesimals disk or the test particles, and this also does not solve the problem. So we really it changed almost every parameter that we can reasonably change, and this problem persists. You can either get a gray scattered disk as observed,
Right.
or you can get a red plutinoise also as observed. It was in no models, no matter the parameters we tried, we were able to get both. And this is really an open question, since we were not able to solve this tension between these two.
Yes, I'm with you. Very good.
So, so this is really one of the open questions of the paper. Maybe you can go back to this later toward the end, but really this is one of the questions that we were not able to answer. How do you reconcile both, given that we tried all sorts of models? So maybe the structure of the model should be completely different. Maybe Neptune's migration should be completely different than imagined. Maybe the other planets should be doing some stuff other than what we consider them to be. Maybe the planetesimals disk was wildly different than what we thought.
Right.
Who knows? Maybe it's planet 9. Maybe
gonna go there. I was gonna go there to planet 9, right? Maybe there's another object out there that's scattered out. Yep.
So yeah, this is one of the open questions left from the paper.
Good.
So I will, however, what I want to do now is go back to the fundamental question, which is what is really the physics controlling the distribution of these red objects? In other terms, what are the physical dynamical effects at play that are stopping these red objects from having high eccentricity or high inclination? So, okay, we looked at it from a color transition point of view, but we really need to understand what's really happening physically. What are the dynamics that are really happening? And this is what I want to talk about right now. So can we go to figure 9, please?
Yes, we certainly can. Figure 9, let's blow that up a wee bit. That's a little too much. Try here. You can always blow up each one if need be.
So we don't really need the small details, I guess. So, okay, so what we want to understand now is what is the dynamical origins of viscosity in red objects at high inclination and high eccentricity. So the first thing we did is obviously to plot the final inclination of well, all of the objects we have as a function of their initial semi-major axes, right? Since the color is fundamentally tied to the initial semi-major axis. And so we did for the eccentricity, just to see what's really happening. So if you look at the top left panel of figure 9, you can see that there is a really clear correlation between the inclination and the initial semi-major axis of objects.
Yes.
So to some degree, this gives you a very hand-wavy maybe way to explain this correlation between the color and the inclination, which is objects starting at smaller semi-major axes are gray by definition, and these interact with Neptune stronger, and so they have higher inclinations. Yeah. While red objects start way further out, they do not interact with Neptune as much,
right? And
so they have lower inclinations. So this really gives you some intuitive way of thinking about the problem. So then, however, if you look at the right-hand side, which is the same for the eccentricity, you can see that you do not have such a strong correlation. You do not see strong correlation between the eccentricity of objects initial measure axis. So you can see that up to an initial semi-major axis of roughly 45 or so, all of the objects reach the same eccentricity.
Yeah.
Right, roughly. So what we noticed, however, is that around 45 AU, there is a sudden and sharp absence of red objects. So you can see this stronger in the bottom right panel where we only show low inclination objects. You can see that there is a very sudden cutoff in the red objects.
Yeah.
Around 5 AU. So this told us that this is really not the end of the story. So there is some very specific dynamics at play here that are causing this absence of red objects with high eccentricity, even if they start at 45 AU. So red objects starting inside 45 AU, they have high eccentricity, but then suddenly something is happening, and then red objects starting at just 1 AU later have much lower eccentricities overall. So we really want to dig deeper and see what's really happening.
Okay.
So we thought to reverse the problem. We thought that, well, why don't we look at it from the other direction? Why don't we choose red objects on high eccentricity and or high inclination orbits, and see how these particles got there? And maybe this tells us about the dynamics at play and why these objects are so rare. So what we did is we took these high eccentricity and high inclination red objects that are really rare, and we looked at their dynamical history in detail.
Yes.
And we looked at so many of them, and we tried to understand what do they all have in common, and try to conclude then what is the dynamics that are suddenly emptying high eccentricity objects.
Right.
So maybe we can go to figure 12, please.
Oh, lovely. Okay.
So in figure 12, we look at the origins of high eccentricity and high inclination red objects. Okay. Since, well, if we understand how these come to be, then maybe we'll understand why they are so rare. Okay. And it turns out there are 3 different processes at play depending on what objects you are looking at exactly. The first objects, and the simpler to understand, are high eccentricity but low inclination objects, red objects. Again, I'm only talking about red objects. So these are the red objects in Q1, in quarter 1, which is the top left in the plot. It turns out each one of these red objects is first captured in its second order or third order motion resonance. Okay. So these are motion resonances such as the 7-4, 5-2, 5-3. These are second and third order motion resonances. And then these objects survive inside the resonance for sometime even up to 1 billion years, sometime for very, very long time. Okay. And then at some point, sometimes due to dynamical diffusion or just chaotic evolution, these objects exit the resonance. Okay. They encounter Neptune and they get scattered to very high eccentricity. Okay. So the mechanism is mean motion resonance, second or third order motion resonance capture. They live in it for a while, then they escape, then they get scattered into high eccentricity by Neptune. So this is how you get the red objects in Q1.
Yes.
So then we looked at the high inclination but low eccentricity objects. These are the red objects in Q3.
Yes.
So it turns out that, so this is the bottom right panel. It turns out that these objects start in the very same way. So these red objects also start in the second and third order motion resonances. Okay. But then they undergo quasi-oscillations. So quasi-oscillations is when, so it's in specific parts of parameter space, objects, well, quasi-oscillations, inside the motion resonances. That's very important. So in some parts of parameter space, objects can undergo quasi-oscillations inside the motion resonance where their eccentricity decreases and their inclination increases periodically. So you have the eccentricity increasing, then inclination decreasing, and both are happening exactly out of phase for a while. But then once these particles are in the high inclination, low eccentricity part of the process, then they can escape the resonance. And so these objects start in the second and third order motion resonance.
Okay.
And then through these this quasi mechanism, their eccentricity decreases, but their inclination increase, and thus they exit the resonance and they end up in Q3. So finally, the last family is Q2, which are objects with both high eccentricity and high inclinations.
Right.
So it turns out, yet again, these objects start in the same second and third order mean motion resonances.
Okay.
However, simply by pure chance, by pure probability, instead of these objects leaving the resonance and getting scattered outward and ending up in Q1, these objects get scattered inward. And then they get scattered inward. And when they get scattered inward, they encounter some given secular resonances. And these secular resonances increase their inclination before they are scattered yet again outward by Neptune, which also increases their eccentricity. So it's the inward scattering plus the secular resonance crossing that increases their inclination, and the final outward scattering by Neptune that also increases their eccentricity. So what do all of these three families have in common? This is really the main question. What all of these three mechanisms have in common is that each one of these particles started in a second order or third order mean motion resonance.
Yes. Good.
And so it turns out that these resonances are really central to creating these high eccentricity and high inclination red objects. So can we go back to figure 9, please?
I certainly can. Figure 9.
So in figure 9, it turns out that if you look inside this blue box where there is a sudden absence of red objects, this is a part of parameter space where these second and third order motion resonances does not cross. And this is why these blue boxes are empty. So you have these second and third order motion resonances, they sweep through the disk. And then at some point when Neptune stops, obviously the resonances are going to stop moving. Right. And so they never cross into this empty area. And so the reason why there is a rarity or absence of red objects on high eccentricity is simply the parameter space to create them is really narrow, because the parameter space to create them is sandwiched in a way in semi-measured access space. On one hand, by the gray objects, so they cannot be formed inside 42AU because this is where the gray objects are, and they cannot form outside 43 to 45AU because this is where these second and third order motion resonances don't cross. Okay. And so the region of phase space, the region of parameter space to create these objects is really, really narrow. And that's why there is a rarity of red objects on high eccentricity. Got it.
Nice. Very cool.
So this is really the second major result of the paper, and well, the third. And this is really the last main result. The first main result is the observational one. There is a rarity of red objects in the scattered disk. The second main result is that to create these correlations, you need a color transition line at 42AU roughly. And the third conclusion is that you create high eccentricity red objects starting from these second and third order mean motion resonances, and their absence is what really leads to the rarity of these objects. And this is really the final conclusion of the final main conclusion of the paper.
Very nice, Mohammed. Nice work.
Thank
Nice.
you.
Very cool. So I want to thank you very much for sharing your very lovely article with us. Very nice. So you touched on it a little bit in the talk, and so sort of where do we go over let's say the next 5 years to help advance solutions to this problem? Are there additional observations coming? Are there new telescopes coming online? Are there additional in-body calculations to do? You know, for example, how would we determine the gray versus red line on that?
So,
or just where do we go over the next 5 years?
well, there are multiple things that are definitely going to happen, which is interesting and very exciting. First, the Colossus observational campaign is ongoing. They're going to definitely get new data, and this might allow us to be more granular when looking at the observations.
Okay.
So instead of looking at the data in this broad red versus gray populations, maybe we can go into smaller subfamilies and see what's happening. If we have enough observations, then maybe we can understand what's happening inside each single dynamical family, and this is definitely going to be very interesting. Also on the observational part, well, we do not know what the color transition is chemically. So this is more ALMA territory, ALMA observations, but I would be really interested in knowing if such a color transition around 40 AU can be constrained, or I won't say observed, but if any light can be shed on it by ALMA observations, so molecular line, etc. And see if ALMA can tell us a bit about what's happening chemically in the far out part of the disk, which is obviously harder and harder because it gets colder and colder.
Right.
But so that's also something that's really interesting. So this is on the observational side. On the numerical side, I mean, there is this tension I was talking about between explaining the abundance of red objects in the 3-2 motion resonance, so the red plutinos, and explaining the lack of red objects in the scattered disk. So we tried so many parts of parameter space and so many numerical simulations, and we were not able to explain both simultaneously. So I would be very, very interested in seeing if, or knowing if there are any outside of the box solutions that we really did not think about, or if it's really simply parts of the parameter space that we did not explore.
Okay.
So that's also something that I really wanna understand.
Okay. Very cool. Very nice. So it's like,
so yeah, these are really the main.
Oops, looks like it froze a little bit there. Okay, I'll pick it up. Well, it looks like there's a lot of some really fun stuff over the next 5 years or so on this topic, and help resolve some of these tensions, to use a modern word, between those two. So, so great. So Mohammed, again, I want to thank you once again for sharing us your really lovely AJ article. And that'll do, everyone. I hope this made your astronomy day just a little bit better, and we'll see you next. Bye-bye.
Again, thank you so much. Have a nice day. Bye.